14.5 curvature and normal vectors. Okay, what are we going to do here? We're going to find the unit tangent vector at a given point on a space curve, which we already defined at the beginning almost at the beginning of the chapter. That is the same way you get a unit vector, divide the vector by its magnitude. But the tangent vector, the unit tangent vector, it's special. Number one, because that's obtained by finding the derivative of the vector valued function, which the analogous to, or the equivalent in scalar functions, you get the derivative to find the slope of of the tangent line at a given point on a given function. Here, it's going to give us the tangent vectors with a little more information. We need to be very specific about the direction of those vectors. That is, it goes in the direction of increasing time. All right, what else are we going to do? To determine the curvature of a smooth parameterized curve. What else? We're going to define the principal unit vector, and here is where we're going to get crazy about. And find the tangential and the normal components of the acceleration. So that's something, a very important tool you will need in physics, in mechanics later. Okay, so, well, again, the unit tangent vector and curvature, so this is just to redefine what it is. I mean, the tangential, find the derivative of the vector value function and divide by its magnitude. All right, and of course, all those vectors have to have a magnitude of 1. Now, so here is the new thing about the new tool, the new piece of information. We don't just want to know the direction of motion of an object. Also, we want to know how fast a given curve is turning. Because, for instance, if you think of a parabola, right, versus a circle. Clearly, closer to the vertex of the parabola, the curvature will have a larger value than a circle, because I mean the curve it's a steeper curve, right? So it's a more pronounced curve. So now, how do we get the curvature? Well, actually, there's a bunch of ways to get the curvature, and in fact, just to give you the heads up. So the curvature, depending on the complexity of the function, actually there will be 2 different ways to calculate it. And when I give you a take-home quiz or a problem on an exam, I will let you know which method or which approach to use, so you don't get to struggle. Because I've seen that in the past, that on a take-home quiz, I specifically say use this formula, use the alternative formula. No, they use the longer method. They end up doing 3 pages of work just to find one result, right? So yeah, I'll show you the advantages and the disadvantages of the different methods. All right, so curvature, which is denoted with a lowercase kappa from the Greek alphabet, that is the magnitude of the derivative of the tangential divided with respect s. That's a lot. I mean, because check this out. Notice the parameter. It's a parameter s. It's not the parameter t. That means that somehow that implies we need to get that vector valued function in the arc length parameter, which we already saw. It may take a good minute. It's not the craziest problem in the world, but it takes time. So, and actually it has to be a positive result, because hey, it's magnitude, right? So, however, there's an alternative way to get the curvature without having to reparameterize with the S parameter, with the arc length parameter, because for the most part, we're given vector valued functions, or we work with vector valued functions with the variable t. So why not find relations or formulations in the same variable? So here we have it. That is the quotient between the derivative of the tangential divided by the magnitude of the velocity, which sounds like a lot, right? And it will be. Okay. So as you will see here, guys, it's going to be very formulaic, because all the tools that we need, we already have them. Derivatives, finding magnitudes. I mean, at this point in time, it's most of those calculations are hopefully a second nature for you. However, it's now how we're going to put together with this new formulations to calculate these properties, like in this case, the curvature of a curve. I mean, okay. So let's find the curvature for the curve. Equals 5 sine t and 5 cosine t. Okay, that looks like a circle of radius 5, and it's oriented in the negative direction. That is in the clockwise direction. Do you see why? That's because we have the sines and cosines interchanged in their positions, in the components rather. Okay, so let me see. Let me leave the formula like this so we can see it. So we're not flipping pages the whole time. All right. So. Number one, we need the derivative and its magnitude. And we also need to find the tangential as well as the derivative and then its magnitude. Okay? So, number one, let's find r prime. That is 5 cosine t, negative 5 sine t. And well, let's find its magnitude. That is the magnitude of r prime. That equals the square root of 5 cosine t squared plus negative 5 sine t squared. Okay, so what is that going to give us? Okay, 5 squared, that's 25. Cosine squared t. By the way, we will be using a lot these relations yielding to Pythagorean identities. You'll see how we're going to use those a lot. So, sine squared t. And that equals, okay, cosine squared plus sine squared. Again, isn't that equal to 1? Times the 25 they both have in common. That's just the square root of 25, which equals to 5. So we have the first part, all right? We have the magnitude of r prime. Let's get the second part. So for the second part, number 2, that is, we need to find the tangential. And the tangential is given by r prime divided by its magnitude. And by the way, we don't need to calculate anything. That's because we already have it. This prime. So r prime, that's what we got in the first part of part 1. That is 5 cosine t negative 5 sine t over its magnitude, which is 5. And to simplify this a little bit, divide out the 5s. That's simply going to give us cosine t negative sine t. Well, how do we know we're doing a good job so far? Well, this BT represents unit tangent vectors. So look at this vector right here. Does that look like a unit vector? Without finding the magnitude. That should look like a unit vector because A, it's cosine and sine. It doesn't matter if one of them is positive or negative. So those are the representations of the points on the unit circle at a given angle, right? So if the coefficients are equal to 1, so yes, that has to be a unit vector. Okay, what do we need? What else do we need? So we got the denominator already. We need to get the numerator. So the numerator is asking for the derivative of the tangential of the unit tangent vector. That is this expression we just got over here. Let's find its derivative. That is negative sine t negative cosine t. And finally, let's find its magnitude. That equals, what's that? The square root of negative sine t squared plus negative cosine t squared. That equals the square root of sine squared plus cosine squared. Again, equals to 1. which is 1. Which actually is a little bit silly that we took the time to calculate this, because come on, what's the magnitude of a unit vector, right? Isn't just 1? So in a way, it's kind of weird to do all that. Okay, well, let's get the curvature k, or not k, kappa of t, that equals the magnitude of the derivative of the tangential. Oh, well, the thing is, in some cases, the derivative of the unit tangent vector may not be a unit vector. That's why it's not a, well, it's silly in this case, but not in other cases. Okay, so that's divided by the magnitude of r prime of t, which we have everything we need. That is the magnitude of the derivative of the tangential, which is 1, over the magnitude of the derivative, which is 5. Let's assess this result and see how it makes, and find out how this makes sense. Notice how we got a constant as a result for the curvature. Why do you think it's a constant value? What is that? It's a scalar. Okay, let's think of the shape, of the geometric shape of the curve we're working on it. So what does that result make sense? The direction comes forward. Mm-hmm.
Like you have the rate of change for the scalar, that's the rate of change for your direction.
Mm-hmm. Yes. Any other ideas? Because it's a circle, right? I mean, it's the same. It has the same curvature at every single point. It doesn't change the how fast the curve is turning. It's a perfect circle, unless it were, say, an ellipse. Well, we would have different curvatures at different points. And like the example I gave you at the beginning, the parabola, it's not perfectly circular, so that's going to have a variable curvature at different times. And I think this is a good place to quit.